Right, this is going to be an optional lecture. It's going to be a bit of a review of a particular element of group theory, specifically involving the concept of cosets, normal subgroups, which are also called invariant subgroups. And ultimately, I'm interested in making sure you remember the idea of a factor group. A factor group. Because this ultimately will become important when we discuss the notion of a covering space and some other things down the road. But the reason I'm doing this as an optional lecture is because I've actually passed this section of Gilmore and I skipped over it. And the reason I skipped over it was because fighting through it paragraph by paragraph was actually pretty difficult the way Gilmore wrote it. And it's non-standard the way he writes it. So I want to cover it in the totally standard way. And then I'll explain my problem with Gilmore's presentation. I'm not here to be a critic of Gilmore's book. I love it to death. The truth of the matter is, though, it's a hard book. And so I had to work through some issues there. So we will, let's get on to this. I'm assuming you know elementary group theory, and this is considered elementary group theory. There's nothing here that's complicated beyond a first semester group theory, but this is the thing that fades the fastest if you don't do group theory regularly, so let's cover it. And let's begin. So the group we're going to work with is the group of the symmetry of the squares. And I'm just choosing this book group just for demonstrations. It's rich enough to get our point across, but it's simple enough to just go through really quickly. And the group of the symmetries of a square is typically called dihedral group 4. It's actually it has 8 elements. The order, I guess the way you would write it is the order of the dihedral 4 group equals 8. The 4 is there to, I believe it's the symmetry of a square that has 4 sides, I suppose. So this is the group we care about. So the idea, just as a reminder, this is actually quite similar to our notion of groups of transformations, right? We have the group over here, and then we have the geometric space over here. And the group contains elements that are transformations of the geometric space. So this element would transform the geometric space, say, by rotating it through 180 degrees, which would take this point and move it, I guess if you rotated it by 180, it would move it here. And this point would move here. And this point would move here. And this point would move there, right? That's just like that. But the point is that after you do that rotation, it's still a square. So therefore, the rotation by 180 degrees is a member of this group. And obviously, rotation by 30 degrees would not be, because then the square would rotate to something that looks like, like this, right? A 30-degree skewed object, which is still a square, but it's not unchanged from its original configuration. So R30 is not an element of the group. So the total elements of the group are 180-degree rotation, 90-degree rotation, certainly a rotation where it's left alone, so the 0-degree rotation. Well, if you have 180 and 90, for it to be a group, you better have a group element ready and waiting for R90 followed by R180, right, which is, of course, going to equal R270. So R270 has to be in the group. Notice R270 does not equal R90 or R180. It's a new element. And of course, a 270-degree rotation would just take the corner over to this corner, likewise all of these others. So each of these 3 rotations are in the group, and no others, right? No others. Now, notice that the group elements have nothing to do with the square, except that they operate on the square, in the sense that the square is not the group, right? The group is the operations, the transformations. That's exactly like our Lie groups, right? So except this case, it's discrete. There's no way to make this a continuous space. There's only a countable, not only is there a countable number of elements, there's a finite number of elements. It's worse than countable. It's got 8 elements. Right? So you're never going to make a continuous group out of this the same way with a real topology. The only topology you could throw down in this is probably the discrete topology, where every function is continuous, and it's not what we're after. It certainly isn't a manifold, right? Which is what's really important. So, but it's still a group of transformations. It's just not a Lie group of transformations. So all of the Lie stuff is, you've got to have continuity, you've got to have a manifold structure, but this part is for real, right? In other words, you have a function f of, say, R90 acting on, some point of the square, right? X, and it'll give you a new point of the square. It'll put you into Y. So R90 would be, I guess, boom, it would go over to there. Okay, but what else? What other members of this group are? We found 4, but clearly if you flip the group along this line, I guess we would call that a vertical flip. You could flip the group along this line, and you call that a horizontal flip. You could flip the group, I keep saying flip the group, flip the square. You could flip the square along that diagonal or this diagonal. We'll call this one D, and then this one D prime, right? And all of these are legitimate transformations of the group of the square that leave the square unchanged. And so all of these are elements of the group. And here's the table. I took a photograph from my favorite old group theory book, which I'm not going to name because it's not like this book is amazing. It's just the one I used when I was a student. So that's why it's my favorite. There's really not much more to it. But the point is, this table is the group operation table. R0 on any element gives that element right back. R0 to the left of any element gives the element back. R180 transformed. R180, let's see, I guess R180 to the left of any element gives you this group multiplication. So R180 times R90 is R270. R180 times R180 is, of course, the identity. So R180 is its own inverse. That's kind of a nice little feature. R180 times R270 is R90. R180 times a horizontal flip is a vertical flip. Oh, that's a good way of checking to see if we figure this out the right way. If this is a horizontal flip, right, if I first do R180 so that this point ends up here, right, and then I do a horizontal flip, then that point ends up there, that's equivalent to a vertical flip, right? Okay, so I think I've defined it the same way this book has. If I haven't, this table will prevail. Then you have the diagonals and the notice that all of the flips are their own inverse, right? So V on V is the identity. Delta D on D is the identity. R0. Okay, so there's our group table for this particular group. All right, so what next? Well, now we want to consider subgroups. Groups that exist within this group, that are subsets of this group. Remember, the group is just a set, right? So the set is going to be R0, R180, R270, R90, H, V, D, and D prime. That set is the group, right? And that set plus the group operation is the group. And you have to show a few other things. Everything has to have an inverse, right? And you can do this for this group. Of course it will. Everything should have an inverse, and everything needs to be associative. But it doesn't have to be commutative, right? So let's see, is this group commutative? V times R270 is D prime. R270 times V is D, right? So we know right away this is not a commutative group because V R270 equals D prime and R270V equals D, right? So those are not the same. So clearly this is not an abelian group. Abelian is the word for commutative group if you don't remember. So we have that little fact going for us. But now we're kind of curious about what subsets of this set are groups in and of themselves, right? Do I need all 8 elements for the group, or can I take a smaller subset and still have a group. And one of the nice things about choosing this as our example is it's pretty obvious that you can just live in the world of rotations and never involve flips. So, is that true? R90 times R90 is a rotation. R270 times R270 is a rotation. R270 times R90 is a rotation, or zero rotation, right? And R90 is a rotation. So all the rotations among themselves actually form a group. And so that is going to be an example of a subgroup. So a subgroup here, all the subgroups, of course, must have the identity. So R0, R90, R180, and R270, those are all subgroups. That is a subgroup. Likewise, if an element is its own inverse, right, then R0, R180, for example, that's a subgroup, right? And R0H is a subgroup, right? Because two H's, H is R0. But then again, you have a subgroup for each of the flips, right? R0V is going to be a subgroup, R0D is going to be a subgroup, and R0D prime is going to be a subgroup. So you got a lot of little subgroups in here. One is pretty large. What about just the flips among themselves, right? For example, H and V, right? I wonder if that'll work. If RH is a subgroup and R0V is a subgroup, then VV is clearly in the identity HH. But what about HV? Well, HV, that's R180, right? That's not a flip. So this nominee set RHV, that's not a subgroup. But if I added 180 into it, well, what happens then? If I add 180, what if I add R180? Well, now I have R180 times V is H, R180 times H is V, H times R180 is V, V times R180 is H, and R180 times R180 is the zero element, which is in the group. And HV and VH are all R180, right? I got all that right. VV is 0, HV is R180. So this, it looks to me like that's a subgroup too. Regardless, the point is you can play this game a lot, and if the group is somewhat intuitive, you can almost guess what the subgroups are, right? Like as in this case. But on the other hand, if you don't study it, you might miss one or two. So the point is finding the subgroups of any given group is an important understanding of the group. You've got to that's part of the problem, is you to figure out the structure of the group means to figure out all the subgroups. Okay, but once you have some subgroups, you can create this idea of the coset. And that's the thing that is a little bit quickly forgotten from the elementary days of this subject. So in this case, let's take a look at a particular subgroup. The subgroup we're going to study is the subgroup R0, R180. It's one of the two element subgroups. And this is no doubt a subgroup. And now we're going to ask ourselves, let's take this group. First of all, let's call that subgroup H. So now I'm going to ask about sets that look like GH. This would be called a left coset of H, where G is any element of the group, right? So the first thing is, what does this symbol mean? H is actually a set. So GH is also a set, and it's a set of G times every element of H. So GR0 and GR180. And this is done from the left, right? G is on the left. I hope I haven't screwed up the left and right coset thing, depending on the notation. Let me check the nomenclature to make sure I remembered it right. Yeah, I got it right. So this is a left coset. A left coset. So this would be the left coset of associated with the element G. So, for example, I could find the less coset associated with R90. So I'm looking at R90H, and I would get R90 times R0, which is R90, and then I would get R90 times R180, which is R270. So R90H is this set here. And that set is clearly not a group at all. It's certainly not a subgroup. It's certainly not a subgroup. It's a subset of the group, but this is not a subgroup, and you can immediately tell because it doesn't have the identity, right? And R90, you don't have the inverse for R90. Well, you do have the inverse. R90 times R270 is in fact the identity. So R270 and R90 is it. Yeah, so you do have the inverse elements, oddly enough, but you don't have the identity, so it's not a subgroup. So now I would look at, say, all right, let me take a different one. Let me take R270. So R270 times R0 and R270 times R180. Well, R270 times R0 is R270, and R270 times R180 is R90. So I actually get the same coset back, and that's really important point. By the coset associated with, so the coset's associated first of all with the subgroup under consideration. So once we've decided what our subgroup is, now we can talk about the cosets associated with that subgroup. And in this case, I've decided I'm going to look for the cosets associated with this subgroup and the group element R90. Well, that turned out to be this set. So this is the left coset of R90 with respect to this subgroup. The left coset of the other element, R270, is the same, right? And I'm going to get the same set as long as in other words, every element of this coset is going to produce the same coset when I go through this process of multiplying every element of H by that element. So R90 and R270 will give you the same coset when I go through this process. This process here, meaning that this is equal to R270H, which has to equal R90H. And it's not that it has to equal R90H as a priori. It's like after I've evaluated R90, I realized R270 was in the set. So I don't need to evaluate R270H because I know it's going to be the same. Okay, so let's try a different one. Let's try, say, VH. Well, VH is going to be, V times the identity is V, and V times R180 from the left, V R180 is H. So I get V and H. Again, it's not a subgroup, and it never will be, right? You can see why this will never be a subgroup, because you're always multiplying by the identity, which is R0, and R180. R180 is its own inverse, so you're never going to find another group element that will give you R0. So whatever group element G you put out here will always give you GR180. And R180 will never be the identity, because that would mean G is the inverse of R180. And remember, we said that this is a subgroup, so the inverse is actually inside this group. I guess that begs the point that if I do R180 times R0, R180, what do I get? I get R180, R0. I get the same set back, right? So when I calculate the coset associated with an element that's inside the subgroup under consideration, I just get that subgroup back, right? So and that's an important point that we'll need later. But so now I have another coset here, a coset VH. What if I did it with D? DH is going to be obviously D and DR180, which I think is D prime. DR180, yeah, it's D prime, right? D to the left of R180. This is the left and this is the right, so that would be DR180 is indexed this way on this table. And that, of course, gives me the other coset of D and D prime. Now, I think I've got it all, right? I've got a coset with D and D prime. I've got a coset with V and H. I've got a coset with R90 and R270, and I've got a coset with R0, R180. That's 2, 4, 6, 8. So all the elements are in cosets. But you'll notice, very important fact, none of these cosets have the same elements, right? These elements here are different from these, are different from these, which are different from H, right? The underlying subset. And that's important because what that means is that the cosets, all of the cosets associated with a subgroup, partition the entire group into cosets, right? It partitions the entire group into cosets. What's wrong? What's going on here? So and here's the partitioning. It's been conveniently arranged on this table already because this chapter is illustrating this point. So this is a coset, this is a coset, this is a coset, and this is a coset. You'll also notice that all the cosets have the exact same number of elements. So these 2 points are really, really critical. If the cosets all have the same number of elements, and it's pretty obvious that that number of elements is equal to the order of the subgroup, right? So, and it partitions, so there's no intersections. It partitions the set, and it partitions it into the same number of elements. And therefore, what this means is that the number of elements in the group, in this case is 8, right? That must be divisible by the number of elements in any subgroup, right? The order of the group must be divisible by the order of any of its subgroups. That's called, I think it's called Lagrange's theorem. Lagrange's theorem. I better check. Yes, it's Lagrange's theorem. And that's a huge thing, right? That's just an important point. It's not obvious, but this whole thing about cosets is one way to prove Lagrange's theorem. Okay, so the cosets partition the group. That's important. The cosets themselves are not groups except for the first one, which is the subgroup that actually defines what the cosets are. You can't define cosets unless you have a subgroup to begin with. That's what enforces the partitioning, right? So that's the definition of a coset. But before I move on, let me point out one thing. When you're dealing with a group, any group, in our case, D4, I never talk about, you don't talk about the coset, right? The coset doesn't make any sense because there are as many cosets as the order of the group divided by the order of the subgroup involved. There are left and right cosets, plural, right? So you're always talking about it plural, right? The cosets. There's a little s there. The cosets of a group. So that's really important to understand. Now, it can be that a group has no subgroups, and no subgroups means it's its own coset, right? You could have a group so small that there's no proper subgroups. Like, for example, if you just had, R0 and V, right, is isomorphic to a really, really, really simple group. This group itself, R0V, is a subgroup of D4, obviously, but it has no subgroups other than just R, right? And the whole group itself, right? So it's only got the two trivial subgroups, the set of just the identity and the entire group. So it can be that a group has no subgroups. It still does have cosets according to those groups, though, right? The coset would be, R0 would be the subgroup, the trivial subgroup, and then V would be the only coset. So you can still get cosets out of the trivial group, the trivial subgroup. All right, so now let's take a quick look at a different subgroup. Let's focus on the subgroup. Let's see, R0 V. How about R0V? I noticed that I call this thing H, but H is also the name of one of the group elements. That was kind of unfortunate, but I don't think it caused any confusion last time. But let's go with R0V as our subgroup, and I'll call that subgroup N, right? So I'm interested in the left cosets of N, which I write as Gn. Gn is a left coset. I have to substitute G for some group element. So let's just go with D prime. D prime N is going to be basically D prime multiplied by each of these two guys in here, right? So that will be obviously D prime is the diagonal flip, and then D prime on V from the left, right? So D prime on V from the left is R90. So I will write R90. And there's a coset, a left coset of this subgroup. But I want to make it clear, there's right cosets also, right? G and G, right? Which would now be N D prime, where I would multiply R0. Of course, I'm always going to get the D prime, whether I multiply it from the left or right on the identity element. It's that other element that could be different. And that would be VD prime with V on the left. So VD prime, and that's R270, right? R270. So what's important to see here is that the coset, the left coset, D prime N, does not equal the right coset, N D prime. These are different objects. And that's why for non-commutative groups, it's really, really important to know whether you're talking about left cosets or right cosets. So I want to emphasize that. So, but it's still the same rules. All the rules apply. It still partitions everything, whether you do left or right cosets. And everything we discussed a moment ago applies to either set of cosets. But there is this unusual circumstance. I shouldn't call it unusual. It's not strange. It's not that unusual. But there are circumstances where you have groups where the left coset does in fact equal the right coset. And in fact, you can rewrite this as G n G inverse equals N. Right? And when you see this, what you're actually saying is that this subgroup, this is the conjugate by G of every element in the subgroup, right? The conjugate by G. And that ends up equaling the subgroup itself. That's not always going to be true, right? If I take a subgroup and I take every element, I pick an element G that is or is not in the subgroup, but probably, let's take an element G that's not in the subgroup, and I find the conjugate of every element in the subgroup, I better get back the same subgroup for this to be true, right? But that usually won't happen. When it does happen, it's also true that the left and right cosets are the same cosets, right? Which we saw here were not. So this, by the way, this conjugation idea, if I have an element of the group X, its conjugate by G is GX G inverse. Sometimes you'll see G inverse X G. It's not a problem. It's convention. But this is the conjugate element. So clearly, if I'm dealing with a subgroup, R, which one am I playing with here? RV, R0V, right? If I wanted to find and I called that's N. If I wanted to find the conjugate of N by D prime, I would say, okay, that would be D prime R0 D prime inverse, which is D prime again, and then it would be D prime V D prime inverse, which is D prime again. Well, this, of course, is just D prime, which is equal to R0, right? But this is D prime V D prime. Now, because of associativity, it doesn't matter which I do first, D prime on the right or D prime on the left. So D prime V is R90, and then D prime V is R90, and then R90 D prime is H. So this ends up being, that equals H. So so D prime N D prime inverse equals the set R0 and H, right? And you'll notice that's not the same set, right? That's not the same set we started with. Therefore, this particular subgroup, R0V, does not have this property, where the left and right cosets are the same and where its conjugate by every element, this has to be true for every element in the group, equals the set n. So the point is that when this is true, we consider n to be a special kind of group. And that special kind of group is called a normal or invariant subgroup. And normal or invariant subgroups, normal, this is the same concept, same words, or different words, same concept. They're very important because they allow us to define something that's really important called factor groups. So I'm going to illustrate this idea of the factor group using this table. And what I've done is this table's already designed to help us understand this concept. So the first thing is we need to find a factor, we need to find a normal subgroup in order to understand this idea of factor groups. And the subgroup I'm going to test is the subgroup R0, R180. And you can see this table is sort of already designed to facilitate what we're doing. R0, R180 is a two-element subgroup, but unlike RH or RV, it actually has the property that that we're looking for, which is that Gn equals Ng, or alternatively Gng inverse equals n, where n is understood to be the whole set. So I've checked it, right? So R0, Rn is obviously R0, R180, right? In other words, this is a group, so any element of this group will be inside this group, so it's certainly going to be the case that the left and right cosets are the same. Not that you have to check, right? We already know that once you have a coset, you've checked it for one of the elements in the coset. The other element's going to produce the same coset, right? That's the whole point of the partitioning. But I checked R90n is R90, R270, so therefore n, and then R90 is also R90, R270. I checked. So this is true for R90. It must also be true for 270, the other element of the coset. Hn is Hv, Nh is also Hv, Dn is Dd prime, and Nd is Dd prime. So that's everything, right? We've checked it for everything. Once you understand that if I checked it for H and V shows up in its coset, then it's also good for V, right? So R0, R180 is in fact a normal subgroup. So what's our next step? Well, once we have identified a normal subgroup, and once we've identified the cosets of the normal subgroup, I'm going to take this weird step of abstraction, and this is the part that confuses the hell out of elementary students. I had no trouble with it when I studied it. I had trouble with a lot of other things, but for some reason I took to this. But what I'm going to do is I'm going to take each of these cosets, right? That coset, this coset, this coset, and this coset, right? That's 4 cosets. And I'm going to give these 4 cosets their own name, right? I'll call it R0n. I'll call it R90n. I'll call it Hn, and I'll call it Dn, right? And those names are now going to, I'm going to make a set of, I'm going to create the set of those cosets. So I'm going to take a set of R90n. Well, hold on. I'm going to take, the first set I'm going to do will be, I guess, we'll call it R0n, because that's, and then I'm going to go R90n, and then I'm going to do Hn and Vn. Now understand these are all sets, right? These are sets, and I'm now having a set of sets, right? And the other thing is I could have said NR0 and NR90 and NH and NV in this case, because N is normal, those are the same, right? There's no difference, right? So once I create this set, I can now, because this is a normal subgroup, this set can actually be understood to be a group in itself. I just need to understand what the group operation is. And that's what this little chart here is all about, right? In this case, what I'm calling N, he called K. I probably should have used K. He's calling script K. So there's R90K, HK, and DK, right? Isn't that what I did over here? Let me make sure I did the same thing. Oh, I said D. I said V. I meant D, right? V is in the same coset as H, so Hn equals Vn, right? So that's not good, but I meant D. Okay. So well, at least he gets it right, or this book gets it right. So now, if I take those cosets and treat them as group elements, I can create a group operation table where the rule for multiplication is that the elements of this coset, when multiplied by any element in this coset, will produce an element in that coset. The elements in this coset, when multiplied by any element in that coset, will always give me an element in this coset, right? So and that is to be understood from this table, right? This coset here, taking any element in this coset, multiplying it by any element in, say, that coset. Actually, I should go the other way around. I should say any element in this coset multiplied by any element in that coset gives me one of these four elements. But these four elements are always in this coset, right? So I simply make that substitution in the table. I say R90 times anything times H, or H times anything, HK times anything times R90K will always give me something in DK. Likewise, DK times R90K will always give me something in HK. R90K, now notice the important thing to notice is that, well, what we just noticed is very important, but another key thing is R90K, I guess I'm calling it N here, and they're calling it K here. Right? That was a little pedagogically sloppy of my part. I should have, if I knew I was going to use this chart, I should have stuck with the same name, but it is what it is. R90N times anything in R0N, right? Where R0N is the normal subgroup that all of this flowed from, right? All of these cosets were created based on this subgroup, and this subgroup is normal. But R90N times R0N always gives me back R90N. Hn times R0N always gives me back Hn. Dn times R0N always gives me back Dn, right? R90, what's its inverse? Well, the inverse of R90 is still R90, right? Because every element in R90, R90 times R270, right, is the identity. R90 times R90 is R180, and R180 is in the normal subgroup, right? So R90 times R90 always returns an element of the normal subgroup. And in that sense, R90 is its own inverse, right? Because we're going to treat this normal subgroup as though it's some kind of identity element based on the principle that any subgroup, any of these cosets multiplied by the normal subgroup returns the same coset. And the same is true. H is its own inverse in the sense that H times H always gives you either HH gives you R0, HV gives you R180, and so those are the only two things you get by multiplying HV times anything in itself. So you always get the normal subgroup back. So there's not much interesting going on here in the sense that every one of these groups is its own inverse. So you always see the diagonal in this case is always going to be, the diagonal will always be the invariant subgroup that spawned all of this. So that's what this chart is. So this chart just cuts to the chase and just says the elements of this group multiplied by the elements of that group will always produce an element in this group. The element in this group multiplied by the elements in this group will always produce an element in this group, right? And then you can see K acting as the identity, meaning the element of this coset times, or K times any element in this coset gives me that coset back. This coset times any element in this coset, K on the left, times this times the subgroup on the right always gives me H back. So the fact that these repeat on the horizontal and vertical first line is indicative of the fact that K is acting as an identity operation. And then everything else just follows ultimately from the ultimate multiplication table of the fundamental group. So the point is that this is a group, and that group is called the factor group, right? And obviously the factor group is not the same as the underlying group. The factor group certainly is not equal to D4 at all. It's too small. It's half as big. It's some other group, and it's a very important concept. And it's going to be called D4 / K, right? So that's the name of the factor group. And we can do this again. Here's another example of a factor group. This is a group of permutations. It's a more complex group where the group elements are just, this chart is really simple. The group elements are actually called, this is just a weird multiplication table that represents a group. It's actually some complicated permutation group called A4. And it's just boiled down into a bunch of strange multiplications that like 6 times 6 is 11. But ultimately, this group, this is a normal subgroup of this group. These are the cosets of this group. And this group boils down to this group right here when you take its factor group. The group can be boiled down to this when you take its factor group. So that's cool. So that's the important point to understand, is to really get a handle on what a coset is, how to figure out what the cosets are, the idea of left and right cosets being the same, and understanding how when you find yourself a normal subgroup, you will always have that normal subgroup will always produce a factor group. Now, the rest of this talk, I'm just going to quickly make the proof. So if you're interested in the proof of this, that's cool. And then I'm going to show what I believe to be an error in Gilmore that I think is very, very important towards the end of this. All right, so let's execute the proof here. We start by formulating this. G is a group. H is a normal subgroup of G. That solid triangle, that's meant to mean normal subgroup. So it looks like a real triangle, like that. And then we define the set that we're interested in is this factor group, which is the set of all the cosets. A times this normal subgroup where A is an element of G. So AH represents a whole set because H is a subset of G. AH is the coset associated with A. So we're having the set of all the cosets. Now we want to show that this is a group, and the group operation is given by this. It's given by AH, which is one element of the group, multiplied by BH. This is the group operation. Sometimes you could put a little circle there to say that this is the group multiplication operation. And that is going to equal AB times H, where now AB is two elements of the group G, so that multiplication is done using the group G's operation, and whatever element that turns out to be, it has a coset, and that coset is given by ABH. And that's basically what we just kind of went through saying in our demonstration earlier. So we need to prove this. So the first thing I have to do is I have to show that if I take an element of this set and I take a second element of this set, right, that I can create a mapping back into this set that's truly a function, which means it's going to be one-to-one and onto, right? It has to be a perfect function right onto itself. I have to prove that this mapping does that, or this operation does that. That's what this is, right? This is an ordered pair, like you take one element, you take another element, take one element, take another element, you get a third element, you get a third element. That's what I have to show. All right, so before I go on, let me point out this notion of coset representatives. So if I have a coset, say I have a coset with the elements A, I'll number them, A1, A2, A3, dot, dot, dot. And there's, say, n elements, A, n, right? That's one coset. So how do I write down that coset in shorthand form? Well, I could certainly write it down as A1H, but I could also write it down as A2H or A3H, because remember, the coset partitions the set. So any one of these elements could be the multiplier of the normal subgroup that gives you this coset, right? We're going to only talk about H being a normal subgroup. So when I do this, when I talk about the whole coset, here I'm using A2 as the coset representative. That's the element of the coset I'm using to sort of call out the whole coset by putting it as the product or the factor in front of the invariant subgroup H. I could choose any one of these elements to be the coset representative. The only time where there's some really strict favoritism for choosing a coset representative is when the subgroup H itself. The subgroup H itself always has the identity element, which sometimes is written E, and then a bunch of other elements. And whatever that identity element is, that's usually the coset representative for the invariant subgroup itself. So in our last case, for example, it was R0H, right? So these are called coset representatives. The choice is completely arbitrary, right? It's arbitrary in the sense that it really doesn't matter what you choose. But what's important about that is if you look at the way the group operation is defined, I'm using A as a coset representative. So this here is a coset, but I've chosen A to be a representative. B, I've chosen B to be the representative, and I'm saying that this coset times this coset is always going to be the coset whose representative is AB, which may be one of these cosets. You know, if A is the identity, then it certainly will be. I'll show you that in a moment, but this is sort of the rule. Obviously, the question is does this matter which representative I choose? So we already know that A, the coset of AH, let's say there's two representatives, and I take out another one, A prime of H. And then I consider the B coset representative of H, of the coset BH, and a different representative, B prime. So these are both the same cosets. A and A prime are both members of those cosets, but I'm choosing to represent the coset using two different representatives, right? So, and the reason that's important is, if this depends on what representative you use, then this isn't going to make any sense, right? It's not going to work. Every identification would be different, right? This has to be irrespective of what representative I choose. So how do we do that? Well, I know that if this coset is the same as that coset, I know that there is that this coset contains A prime, and some other elements. But remember how the coset was derived. The coset was derived by me taking A and multiplying it by the members of H, H1, H2, H3, etc., right? And that gave me A prime, and all of these things. So I know that there is some member of H, when multiplied by A, that'll give me A prime. So I can always write A prime as A times a member of H. So I can always write, let me move everything down a little bit. Hold on. Like that. So I can always write this as A times H1 times H, right? So because AH1 is going to equal A prime, right? Because that's just how these cosets work, right? A times something in here gives me A prime. Likewise, of course, this can always be rewritten as B times some other element, H2, which gives me H. It could be the same element, but we know that there is an element which we will call H2. So now I will write this down using these facts. I will write Well, let's see. What I'll actually do is I'll write this down, A prime, B prime, because it has to be true for any representative, right? So it's true for the unprimed representatives, right? And it will be true for the little primed representatives, right? So I'll write it down using this fact. So this, the way I've written it just there with those primes, is going to be AH1H, right, times, times BH2H, right, which is supposed to equal AH1BH2H, right? That's how that would have to work. So now we just kind of look at this, right? H2H is the coset of H with respect to H2, but H2 is a member of H, right? So that's just H itself, right? So I can immediately just take that and write H, and I get AH1BH. But H is assumed to be a normal subset of G. So that means BH equals HB. So now I can take that and write AH1HB, right? I make that replacement. And then I can write, well, H1H is just H because H1 is a member of the underlying subgroup, right? It's of the underlying subgroup. So this becomes AHB, but then I use this fact again, and I restore it to ABH. So what this is telling me is that no matter what representative I choose to represent the coset, I will always get the same result product coset. In other words, even if I chose A prime, B prime, I get A prime, B prime, H, but that will always turn out to be equal to ABH for any two other representatives AB of the coset. Because remember, this A and B were defined through this relationship that they were related because they were both in the same coset. Okay, so that's as far as I want to go with this. It's a big reminder on how these factor groups work. This will become relevant somewhere down the line for our study of Lie groups. I do want to end this with a warning about some material in Gilmore. So let me do that. All right, guys, so here's the problem. It's on page 73. His definition, we look at the properties of a quotient called GH, right? He hasn't fully introduced what that quotient is yet, but H is a subgroup of G, so we're good there. We have studied this. Such structures are called cosets. Well, I'm kind of complaining already because he really doesn't reference the structures, so there's kind of I guess, new kinds of algebraic structures, right? But here's what he says. A right coset is the set of group operations, C0, C1, and something in G, with the property that the normal subgroup times each of these elements of what he's calling the coset adds up to G, right? So basically, if you look at this carefully, what he's saying is if I have my subset H, let me write this bigger. If I have my subgroup H, with the identity H1 through Hn, right? I have that subgroup. I can take the element C0 multiplied by that subgroup, an element C1 multiplied by the subgroup, and C2 multiplied by the subgroup, which I'll now just write H, and then C3 multiplied by the subgroup. And what happens is we know already that this is going to produce a coset, this is going to produce a coset, this is going to produce a coset, and this is going to produce a coset. Now, if I just randomly pick these numbers, a lot of these cosets are going to be redundant, right? Because if I pick C1 and C2, which are in the same coset, then this C2H and C1H are going to be the same set, so it'll be redundant. So he gives this further restriction. No element of G is contained more than once in the sum on the left, right? And that's the way he's saying is that I only want one coset representative from each coset. And that collection, right? Here's the problem. He takes this collection. I don't see any other way to read this, right? This is the collection that he's calling a coset. And he's not even calling it, I mean, he often talks about the coset sometimes. Clearly, he's suggesting that there's many different ways of choosing C0, C1, and C2, and C3. And of course there are, because you can choose any element inside the coset to be the coset representative. The problem is we're defining the coset this way, and he's got some weird vertical definition of a coset, which really involves one representative from each coset. And all I can say is this. The definition that I just went through with you for the earlier part of this lecture, that's the correct definition. I have never seen his version of this definition anywhere. Remember that whole problem we had earlier on in this course where he defined a field as being a non-commutative or commutative field? That was actually forgivable. I mean, I can go back and there are plenty of places that talk about skew fields, and they're very similar to what he defined, which was called a non-commutative field. So that's fine. And it's also quite harmless. It's purely a semantic question. This is just wrong. So I don't know any other way to say it. I've looked at it a million different ways. If anybody sees some other angle here, let me know. I'll be happy to take this lecture down and fix it. But I'm pointing out that if you're trying to follow along in Gilmore and you get to this part of the chapter, you're going to notice I skipped it because I spent a lot of time digging through it trying to make sense out of it. And, you know, I've read this book a lot, but I never really read through this chapter with the kind of detail that made me call this out. But now I'm calling it out. So this is not a coset. What this is called, when you pick a set, right? When you pick a set of coset representatives like C0, C1, C2, such that C0H plus C1H plus C2H, etc. equals G, that's called a traversal. That's called a traversal. So I don't know. I don't know how to fix this. But here's the real problem. What's even worse is that not only does he misidentify these cosets, but then he makes the claim, which is basically, to my ears, just bizarre, that if you can always choose the elements of what he's calling a coset, what we call a traversal, you can choose these elements in such a way. Remember, these are group elements. These are all elements of G. So he says you can create this coset under his definition and choose these elements in such a way that they form a group. And that group is called the factor group, right? By this normal subgroup. There's still a normal subgroup involved, right? There's still that. So by that normal subgroup, I guess I should use H here. So he's basically saying you can find elements in the group G, right, that correctly picked are a group, and that group is the factor group. And look, that's just not true, right? It's just wrong. Let me see where he actually says that. Yeah, here it is on the next page, right? This theorem right here. If H is an invariant subgroup of G, right? So far so good. Then the coset elements C0, C1, C2, right? So notice right there that's kind of weird, right? Because the coset elements, it's the coset elements he's talking about, right? But we don't talk about the coset elements. We know that there are several cosets in a set, right? But he doesn't. He just takes he takes all of those things. He doesn't even give those things a name. He just takes those things, pulls one element out of each, and calls that C0, C1, C2, and then he puts those guys in a set, and he calls that the coset, and that's these guys. But then he goes on to say that these coset elements can be chosen in such a way that they are closed under multiplication and form a group called the factor group. Right? Notice the implication is that every factor group would under this rule, be a subgroup of G, right? Because if I can choose elements in G that form the factor group, then every time we have a factor group, it's actually a subgroup of G, and that's not true. That's not true at all. And in fact, you can go back to the dihedral group here to see that you cannot choose a representative of these groups to form a group, right? R90 times R90, right, is R180, right? So if I put in R90 as one of the as the coset representative here, I would need, in order to form a group with R90, well, R90 times itself is R180. I would need R180 in it. But R90 and R180, but R180 is in the normal subgroup, and for that representative, I need R0 in order for this thing that I'm trying to build, according to Gilmore, to be a group. It needs the identity. So right away it fails. So it doesn't work for this at all. So I have no idea what he's getting at. Now, it turns out that this error of his doesn't propagate very far, right? Ultimately, his theorem on the factor group regarding connected components of a Lie group, that's all correct. It's just this weird definition of a coset and this just blatantly incorrect theorem. I just don't know quite how to get at it. Now, look, I got to admit, there's some possibility that I don't understand what's happening here, that I just am not reading it right. This book isn't meant for higher mathematicians. I mean, it's not an easy book, but just the idea here alone, right? Just understanding that if just by reading this theorem the way it's written, reading this theorem, clearly these are group elements, and he's implying that these group elements can be chosen in such a way that they form the factor group. That immediately implies that the factor group is always a subgroup. How do you write subgroup? A subgroup of G, right? Or maybe the other way around. Is always a subgroup of the underlying group. And that's not true. That's incorrect. That there's definitely groups that the factor group is not, in fact, a subgroup of the group. Anyway, so that's like a pretty serious error, and I feel awkward calling it out, but I just noticed it, and I kind of worked hard on it. I even skipped this section just because I was trying to get to the bottom of it. But if you see where I'm getting this wrong, if you're following along and you understand this stuff, go ahead and let me know. It's like I said, it's not worth harping on. That's why I'm throwing it at the end of an optional lecture here. But just keep in mind as you read this, if you find it confusing and you can't get to the bottom of it, don't blame yourself. There's definitely a problem with Gilmore. And there's a later book that Gilmore writes where he doubles down on this. So I have to feel like he's trying to say something in a complicated way that we might be missing. But anyway, the way I expressed it, the way I taught it here, this is all the standard way, right? Understanding cosets in the fashion that we did it here, that's completely correct, universal language, very standard stuff. Okay, so I'll see you next time when we move back on to the subjects relating to the generators.